Can tiny nanoparticles literally generate electricity from sunlight? And how does simple molecules link up to build the incredibly tough plastics and advanced materials we rely on every single day? Welcome to This Explainer. Today we're doing something really cool. We're bridging the gap between the absolute nanoscale of solar energy and the macro world of structural engineering.
Think of this as your digital smartboard masterclass. We're going to dive deep into quantum dot solar cells, or QDSSCs for short, and engineering polymers. We'll unpack exactly how these smart systems work, literally from the atoms up.
Here's our game plan for today. We'll start with the basics of quantum solar cells, look at their pros and cons, and then pivot right into polymer science. We'll hit molecular weight, polydispersity, check out some real-world applications, and cap it all off with a focused exam revision.
Let's get right into it with Section 1, Basics of Quantum Solar Cells.
To really understand this tech, we have to zoom way down. By definition, quantum dots are nanoscale semiconductor particles. We're talking just 2 to 10 nanometers across. That is unfathomably small. And because they're so tiny, the electrons inside are squished. They're confined in all 3 dimensions. They can't move freely like they do in a normal bulky block of material. Instead, they get locked into discrete energy levels. This restricted behavior is so unique that scientists actually call them artificial atoms.
And here is where it gets absolutely fascinating. This illustrates the quantum confinement effect in action. In bulk materials, you have standard, continuous energy bands. But look what happens as we shrink the crystal size down. The band gap, that energetic space between the levels, actually gets bigger. A smaller quantum dot forces a larger band gap, which means it absorbs and emits higher energy light. You can literally see the emission shifting from red to blue simply because the physical dot got smaller. We are tuning a material's optical properties just by changing its size.
Moving on to Section 2, QDSSC Advantages and Limitations. So, how do we use these artificial atoms in the real world?
Well, we basically build a chemical sandwich. This is the core structure of a quantum dot sensitized solar cell. Sunlight comes in and hits the photoanode. That is a porous network of titanium dioxide, or TiO₂, coated with our star players, the light-absorbing quantum dots. On the opposite side, we have a counter-electrode, and sitting right in the middle is a liquid electrolyte, usually a polysulfide mix, which is there to complete our chemical circuit.
So how does it actually make power? Step 1. Sunlight hits the quantum dot, and it absorbs a photon. Step 2. That energy excites an electron, bumping it all the way up to the conduction band. Step 3. Thanks to some very clever energy alignment, that energetic electron is injected straight into the porous TiO₂ network. Step 4. The electron races through our external circuit, which is what actually powers our devices. Finally, Step 5. The electrolyte steps in, donating an electron back to the quantum dot to reset the whole system, and the cycle repeats seamlessly. Now, you might be wondering, why go through all this hassle? Why not just use standard silicon panels? Well, this graph tells the whole story. Standard silicon is incredibly wasteful. It completely misses a ton of high-energy UV light, and it totally ignores low-energy infrared. But when you pair perovskite with quantum dots in a tandem cell, it's a completely different game. You capture the UV and visible light, while those quantum dots soak up the near-infrared. It's a much broader, vastly more efficient way to harvest the sun's energy.
To quickly summarize the trade-offs, the big wins for QDSSCs are that tunable bandgap and the broad-spectrum absorption. Traditional fixed bandgap solar cells just can't compete with that flexibility. But as engineers, we have to be realistic about the limitations. Right now, QDSSCs battle long-term stability issues and potential liquid electrolyte leaks. Conventional panels might be rigid and cost more to manufacture, but they are incredibly stable. All right, let's shift gears. We've conquered energy generation. Now let's talk about the physical materials we use to actually build things. Welcome to Section 3, Introduction to Polymer Science.
At its core, polymer science is basically microscopic Legos. You start with a monomer. That's a small, single-repeating unit like ethene. Through a chemical process called polymerization, we link thousands of these tiny guys together to form a massive, continuous chain called a polymer. Think polyethylene. We're taking incredibly simple chemical links and transforming them into the tough, flexible plastics that literally shape our modern world.
But here's the catch. The properties of your plastic depend entirely on how those long chains are physically arranged. Enter our keyword, crystallinity. This simply refers to how neatly ordered and packed the chains are. If they are packed super tightly in a highly ordered way, you have high crystallinity. That gives you a rigid, strong, chemically resistant material. But if the chains look like a tangled bowl of spaghetti, which we call amorphous, you get something highly flexible and impact-resistant, kind of like a rubber band.
Next up is Section 4, Molecular Weight and Polydispersity. Let's look at the math behind this, but we'll keep it totally focused on the practical engineering side. When you manufacture polymers, the chains don't all come out the exact same length. It's a massive mix, so we use two different averages to figure out what we're working with. First is MN, the number average molecular weight. This is just the average size based purely on the total count of molecules. Then there's MW, the weight average molecular weight. This one is really crucial because it gives extra mathematical weight to the heavier, longer chains present in the mix. So why do we care about the difference? Well, here is the golden rule for engineering. MN tells you the average size, but MW is what actually dictates the real-world strength of your material. A higher MW means you have more long chains tangling up together, and that drastically improves your material's tensile strength and viscosity.
We actually combine these two averages into one super important metric called the Polydispersity Index, or PDI. It's just MW divided by MN. A PDI of exactly 1 is the absolute holy grail. It means every single chain is perfectly uniform. In the real world of manufacturing, the closer your PDI is to 1, the more predictable, uniform, and easy to process your material will be.
Section 5. Applications of engineering polymers. How does all this microscopic chemistry play out when you're actually building things? Let's look at 3D printing.
You've probably heard of these three major filaments: PLA, ABS, and nylon 666. If you're just doing some easy, eco-friendly prototyping, PLA is your best friend. Moderate strength, low heat resistance. Need something tougher? ABS gives you that high impact resistance for durable, functional parts. But if you're building serious, load-bearing industrial parts like gears or bearings, you reach for nylon 666. It boasts very high strength and high heat resistance, all thanks to those incredibly strong intermolecular forces we talked about earlier. Section 6. Exam focus and final revision. Let's lock in everything we just learned. Okay, imagine this exam question. You need to design a 3D printed component that's going to sit right inside a car's engine compartment. It is going to face extreme heat, cyclic stress, and chemical exposure. Based on crystallinity and thermal stability, do you choose PLA, ABS, or nylon 6,6?
Here is exactly how you nail the answer. Nylon 6,6 is absolutely the optimal choice. To get full marks, you need the right keywords. Explain that its high crystallinity creates tightly packed chains with strong intermolecular forces. That's what gives it the thermal stability to survive intense engine heat. And make sure to point out why the others fail. PLA would just melt and degrade at those temperatures, and ABS lacks the chemical resistance needed to withstand harsh engine fuels and oils.
Let's wrap it all up with our one-page revision. For energy, remember QDSCs. Quantum dots act as light absorbers, shooting excited electrons into TiO₂ through a circuit and regenerating via an electrolyte. Their tunable bandgaps absolutely crush standard silicon for broad spectrum absorption. For materials, polymers are massive chains of repeating monomers. Remember your variables: MN for size, MW for strength, and PDI for uniformity. And for 3D printing, PLA for simple prototypes, ABS for tough parts, and nylon 6,6 for extreme strength and heat resistance.
We've covered a lot of ground today, from harnessing the sun's energy with 2-nanometer artificial atoms, all the way up to engineering massive, tangled polymer chains that literally build our physical world. The underlying chemistry connects it all. So the question I'll leave you with is this. From nanoscale energy capture to macromolecular engineering, how will you use these materials to build the smart systems of tomorrow? Keep questioning, keep learning.